All right, welcome folks. Today we're going to talk about more model-free RL. Um, this is a benchmark called the functional manipulation benchmark. It's like meant for testing combinatorial generalization and assembly precision. So if you guys are coming up with projects, it's a nice benchmark to test things on. They have a nice version in Sim, Real, and it's quite hard. So might be a nice tool. Okay, so just to recap, we finished imitation learning. We started doing policy gradient. We covered a bunch of stuff about policy gradient, and today we're going to try and finish policy gradient, maybe. And then we'll go to dynamic programming and model-based RL and so on. And so let's do a little recap. We're going to talk about policy gradient and variance reduction. Then we'll talk about natural policy gradients and having a covariant parameterization. We'll then talk about a class of algorithms called TRPO, trust region policy optimization. Then we'll touch on PPO and some variants, right? Okay, so to recap, we want to maximize the RL objective. We think there's multiple ways to do that, right? So there's gradient descent, which we're covering now. There's dynamic programming. There's model-based optimization, which is like model-based RL. Right? But we're going to focus on gradient descent right now. And so if you look at gradient descent, it's not trivial to do gradient descent on this objective because theta is in the probability distribution during the expectation over. But we worked through the reinforced trick, and we worked out that the policy gradient looks something like this, right? So we said that you can write the policy gradient in the trajectory form as grad log p theta tau times r tau. And when you work out what grad log p theta tau is, it is just a sum. It is a sum over grad log p theta at given st over the whole trajectory, right? Times the sum of rewards in the trajectory. So you can work this out with Monte Carlo samples. So you can compute a gradient by drawing a bunch of trajectories. For each trajectory, you can think of this as drawing a bunch of trajectories. For each trajectory, computing the sum of grad log pi theta at given st along the trajectory, and then multiplying it by the sum of the rewards in the trajectory, and then averaging this over all the trajectories. And so that's what policy gradient looks like. Remember that there's like a bracket here. So in the original form of policy gradient, you're summing up grad logs along the whole trajectory, summing up rewards along the whole trajectory, then you're multiplying them and averaging them. Okay. So what makes it challenging here is that you're doing a single sample estimate, right? So you're saying that like kind of wiggling this rope and you're tying together the fate of all outcomes along that trajectory. Right? And so you're saying that you're only weighting it with rewards in the current trajectory, even though the outcome of a particular state action is now coupled to like unlucky things that happen in the future or bad decisions you made in the future or something else, right? And so it couples together all the actions. It's susceptible to scale variations and to lucky samples, right? And so this kind of like leads to this issue you often refer to as variance, right? So if you compute the policy gradient a bunch of times, you'll get like different gradients, right? So you'll have a lot of variance in your estimator. And the reason policy gradients are so inefficient is that you just need a huge number of samples to reduce this variance. Okay, so the first trick we covered was causality, saying that like in a Markov system, you don't care about the past, right? So you're just going to say, I don't need to worry about t prime going from 0 to t. Like your decisions now can never affect the past. And so you just worry about return to go. Just worry about things from t to small t to capital T, not from 0 to t. Right? So you only care about return to go, not return in the past. And then the second thing we talked about was a baseline, right? So we said that as long as we subtract a state-dependent function, so remember that we're like this sum is going from t prime equal to t to capital T, but your baseline is only dependent on your current state st, right? So as long as it's not dependent on action, not dependent on future states, this will be unbiased, right? And how do we get it to be unbiased? We had the gradient of an integral or probability, which is gradient 1, which is 0, right? That's how we got there. Okay, so that is what we did so far. Any questions? Anything that came up over your weekend of thinking about policy gradient? Okay, so I'm actually going to skip this, I think, but one useful exercise is to say, okay, we said we're going to choose the baseline as like the average value, right? So we said we're going to like try and regress to the average returns from any state. But it doesn't mean that that's the thing that reduces the variance the most, right? So one thing you can do is you can define the variance of an estimator as expectation x squared minus expectation x the whole squared, right? And then you can say that if you have the policy gradient estimator, which is on the right, it's a function, you can compute the variance as a function of b, which is a baseline. Let's say you had a constant baseline, and you can compute your variance as a function of b, and then you can take the gradient with respect to b and set it to 0. Right? And so what that allows you to do is find the optimal baseline, right? The baseline that minimizes variance. Right? And so let's see, um, I'm just gonna skip the derivation, but it looks something like this. Let's see. Looks something like this, right? And so you can um, you can show that there's the expectation x squared minus expectation x the whole square. We don't have to work through this in detail, right? But you just kind of substitute in grad log p theta tau r tau minus b into this estimator, right? And then you'll see that like you'll have two terms. This one is the expectation x squared term. This one is the expectation of x the whole squared term, right? And you'll see that the second term actually doesn't depend on b because the estimator is unbiased, right? So it doesn't change the expectation. And then you just take the first term, you take the gradient with respect to b. You guys can work through the algebra at home, but essentially what it gives you is optimal baseline that looks like this, right? So it says it's kind of like, it's the expected reward weighted by the gradient magnitude, right? So you're going to like, you're not going to just do the average reward. You're going to do average reward weighted by the magnitude of the gradient. So things which have higher gradient will matter more. And so you want to like move your baseline towards them so that you reduce variance. Yeah. So if this is a not like when you said that oh, variance is unbounded. Oh. That is always positive. Yeah. And so, okay, so you can work through this algebra, but this is not the optimal baseline. It's an optimal constant baseline. It is not the optimal baseline that is a function of state. Right? And so, but it's just a useful exercise to think about the estimator variance and like what can reduce the estimator variance. Okay, so that's a recap. Any questions before we keep going? Cool. Okay, so the first thing we're going to do is we're going to take a closer look at gradient descent. Right? And so when you work out policy gradient, you can show that it's just like gradient descent on j theta, which is the expected reward objective. But what is gradient descent? Let's like look a little deeper at what gradient descent is, right? So if you ever have a function, you're trying to do gradient descent, you can think of gradient descent as taking a linear approximation of that objective and then trying to find the maximum of that linear approximation under a quadratic constraint, right? So it's saying that like, if I have this as my current theta I, right? I'm going to take a linear approximation, and then I'm going to say like within this ball, right, where theta minus theta I norm is less than or equal to epsilon, I'm going to try and find the maximum, right? And so to gradient descent, you can kind of think of it as like you're going to construct this ball, and then you're just going to pick the thing that's the maximum. Yeah. And so you take a linear approximation, and then you take a quadratic constraint on the parameters. Right? And so you can work out that this thing gives you gradient descent, right? So how are we going to do that? Take this objective, which is j theta I plus gradient j theta, theta equal to theta I, theta minus theta I, right? And then you can add like a quadratic penalty, right? Take the gradient of this whole thing with respect to theta, set it to 0, right? You're trying to find the maximum. Take the gradient of the whole thing, set it to 0. This term doesn't depend on theta. This term does depend on theta, right? So you get like, essentially what you'll get is like gradient theta j theta, theta equal to theta I, plus alpha times theta minus theta I is equal to 0. right? Might have got the sign wrong somewhere. But essentially, when you move the terms around, you can show that theta is equal to theta I plus 1 over alpha times the gradient theta j theta. Right? And so you can derive, oh, I think I got the signs wrong because my Lagrangian had the wrong sign. So if you basically, the way to derive this is you take this objective, you construct the Lagrangian, right? So you say the constraint optimization you construct as a penalty. And then you take the gradient with respect to theta, set it to 0. And so you'll get theta is equal to theta I plus 1 over alpha of the gradient of j theta at theta I, right? And so if you ever want to derive, you can derive gradient descent as steepest, you can think of it as steepest ascent under the Euclidean norm, right? So it's not steepest ascent under every norm, it's steepest ascent under the Euclidean norm. Euclidean norm as in like, it's theta minus theta I at the L2 norm, right? Okay, so this makes sense. All we've done is we've just re-looked at gradient descent, not as just like some magical entity. It is like steepest descent under the Euclidean norm. Now you could change this norm and you can get different optimization algorithms, right? So you can get a broader class of mirror descent algorithms, but basically you just like construct the penalty, take the gradient, set it to 0, you get gradient descent. Cool. So we can do this. It just gives us the same objective. But what's the problem with this? Why is this not always the best thing to do? Like when might this have problems? Right? And in this objective, I've set alpha to be a step size. I've chosen it as a hyperparameter. But when is this not a great thing to do? Any functions that you have with it as well? Two larger step size. Great. So you guys got both. But the first one is when you have too large of a step size, right? So we chose alpha as a hyperparameter. But if you think of this gradient ascent problem, let's say you computed the gradient, but you went like too far, right? Actually, what you could have is things that get worse, right? And so often this gets worse in reinforcement learning because when you take too big of a step size, you start collecting really bad data. You like never recover from. And so you get into this like bad cycle of taking too large of a step size. Often what happens in practice, you have to take these tiny step sizes and then things become really, really slow. And so large step sizes can cause a problem. And the second issue is it becomes really sensitive to policy parameterization, right? So some parameters make a much bigger effect on the policy than others, right? But you're taking this as a Euclidean norm. So you're saying that all the parameters are weighted equally. You want to say like every parameter, you have like a ball which weights all the parameters equally, but some parameters might be scaled way differently than others, right? And so what happens is like your space might start looking a lot like that. Like one dimension is way more stretched than the other, right? Whereas you want your space, and when you do gradient descent on that space, it tends to zigzag a lot, right? So your condition number is pretty bad, but you want your space to look a lot more like this, right? So you're saying that like your gradients become really sensitive to like the scale of your policy parameterization. So let's take a closer look at what I mean by that. Right? So let's consider this function, L theta, which is theta 1 plus theta 2, okay? So you take the gradient of this function with respect to theta 1, it's 1. Gradient of this function with respect to theta 2 is 1. Right? But now you can like reparameterize this, right? So you can reparameterize it with phi 1 and phi 2, where phi 1 is theta 1 squared, and phi 2 is theta 2 inverse. So then your loss becomes phi 1 to the 0.5 plus phi 2 inverse, right? Those are exactly the same thing. And so this thing to the 0.5 is just theta 1. This thing inverse is just theta 2, right? And so you can rewrite L phi as this, and you now take the gradient with respect to phi 1. You get 0.5 theta 1 inverse. Take the gradient with respect to phi 2. You get minus theta 2 squared, right? Which is a totally different gradient, right? And so it becomes really sensitive to your parameterization. Another way of thinking about it is like in the neural net, there's like a bunch of parameters. Let's say you had like all the parameters in your neural net and then some parameters of variance. And like it becomes overly sensitive to some of those parameters and underly sensitive to other parameters, right? And so what we instead want to do is kind of normalize the effect of the parameters, not by their magnitude, but by their effect on the policy. Yeah. And so what we're going to try and do is kind of get rid of this kind of scaling effect. Right? And so we're going to first try and deal with this sensitivity to policy parameterization. And the second thing we're going to try and do is deal with too large of a step size. Yeah. Cool. Okay. So when you say not covariant, you mean that it's like it's the same for all the policy parameterizations. Right? You want it to be the same. Okay. So one way of thinking about this is like if you think of gradient descent as the steepest ascent on a linear approximation to the objective under the quadratic norm, right? Under the Euclidean norm. You're instead going to say, what if we considered it under a different norm, right? And so let's say you had like some matrix G, right? And you're going to consider the norm under some matrix G. And so you're going to say, I'm still going to do a linear approximation to the objective. And if I can find some matrix G that transforms the space from looking like that to looking like that, then I'm pretty good, right? Because I'm like almost like rescaling the parameters so that the geometry looks the way I want. And so the question becomes, what should G be? But if I had some different norm G, so I'm going to say I'm going to do steepest descent, but I'm not going to do it under the Euclidean norm. I'm going to do it under the G norm, right? And if I can do it under the appropriate G norm, my optimization starts looking a lot like this and not like this, right? And so it'll be a lot more efficient, a lot less sensitive to parameters. Okay, so how do I pick this G? Any ideas? How should I pick a G? The eigenvalues of it have something. Yeah, the eigenvalues do have something to do with the parameters. But let's try to approach it from a slightly more intuitive perspective. But maybe before we work out what G should be, like if you work out the steepest ascent under a G norm, right? You'll do exactly the same stuff you did earlier. You'll say J theta I plus grad theta, J theta I, theta minus theta I minus alpha, theta minus theta I transpose G, theta minus theta I. You take the gradient of this thing, set it to 0, right? And so when you work out the gradient of this thing set to 0, you're going to have like essentially a theta I plus 1 is equal to theta I plus alpha times G inverse gradient theta J theta I. Yeah. So you can think of G as like a preconditioning method. And you're saying that you like scale by the inverse, right? And so things that like matter too much in G, you like rescale them so that they all matter the same, right? So you can kind of think of G inverse as something that like makes all the dimensions matter the same. Yeah. And so if I changed my Euclidean norm to G norm, so like Euclidean norm can be thought of as the G norm with G equal to identity, right? And so then it just literally gives you gradient descent. If you change it to a different G norm, you have a different preconditioning matrix G inverse. Right? Okay. So our mission is going to be to find G inverse. And so let's try to think of what G is good. And what we care about is not the effect of the different policy parameters. We care about its effect on the function, right? The thing that is producing the actions. So we don't care about the parameters as much as we care about the change in the function, right? And so what we're instead going to say is I'm going to still do a linear approximation to my objective, right? I'm still going to do a linear approximation to my objective, but I want to constrain my objective so that like the change between phi theta, the function that is represented by the new parameters, and phi theta I, which is the old parameters, like its probability distributions are bounded. Right? We don't want to just say the parameters are bounded. We don't care about the parameters. We only care about the outcomes on the actions, right? And so what we're going to say is we want to do parameter updates under a linear approximation, but rather than doing the Euclidean norm, we're going to say we're going to have a functional norm. We're going to say we want to constrain the KL between pi theta and pi theta I, right? And so this is what you call a trust region. And so this constraint is what you call a trust region. And so you're saying that you don't want to change outside of the trust region, but rather than having a norm in terms of parameters, you're going to have a norm in terms of the induced probability distributions. Does that make sense? And so you're saying that like the function shouldn't change that much, not that the parameter shouldn't change that much. You're saying the function shouldn't change that much. Okay. So what we're going to do is we're going to say we're going to change from the Euclidean norm to a G norm. We don't know what the G is, So let's try to write it in terms of a functional norm, right? So in terms of the KL divergence between pi theta and pi theta I, right? And then we're gonna show that the second order Taylor approximation of the KL divergence corresponds to something called the Fisher information matrix. So you can kind of think of the Fisher information matrix. All you're going to do is another exercise for home is if you take your KL divergence and write out the second order Taylor approximation of the KL divergence, you can show that it's basically something like that times f times something like that. So the second order approximation of the KL divergence is a quadratic, where your F matrix here is the outer product grad log times grad log pi. Okay, so it's called the Fisher information metric. And it's kind of telling you what's like the sensitivity of your function to different parameters. And so our G matrix that we cared about is actually just this like Fisher information matrix. Right? So remember, it's like if your parameters are, let's say, n dimensional, right? Your Fisher information matrix is like an n by n matrix. Right? So if you have like 100 billion parameters, this is a 100 billion by 100 billion parameter matrix, which is not great. Okay, but the way we got here is we said Euclidean norm to KL norm. The second order Taylor approximation of the KL norm gives us a quadratic, gives a quadratic, which is half theta minus theta I transpose F theta minus theta I, where F is this Fisher information matrix. Right? Everyone kind of with me? So we started with the Euclidean matrix, Euclidean norm. We said that it's like too sensitive to policy parameterization. So we care about functional distance. Functional distance, this thing is hard to optimize, the KL divergence. So you take a second order approximation to it. Second order Taylor approximation gives us this Fisher information matrix. And once you have this Fisher information matrix, then you can plug it back in and you get a gradient update, but something that is just like preconditioned with F inverse, right? So if F is basically your Fisher information matrix, then you're going to do gradient descent preconditioned by F inverse. And that's what's going to like rescale your gradient so that it's not sensitive to the policy parameters, but rather respects KL divergence between pi theta and pi theta I. Right? Okay, so remember, this is just going to be the expected outer product between grad log theta, grad log pi theta, grad log pi theta transpose, which means it's going to be an n by n matrix. And so you have to like precondition your gradient by this n by n matrix inverse. Okay, so this tends to work pretty well in practice. Like, yeah. Yeah, I don't know about the name, but I think you can think of it as it's telling you like how sensitive is your function, how sensitive is your probability distribution to a particular parameter, right? And so the eigenvectors of the Fisher information metric are telling you like which directions is your probability distribution most sensitive to in terms of your parameters. Yeah. So it's the expectation under your current policy pi theta. So every time you have a change in policy, you have to recompute your Fisher information matrix. Yeah. So it's expensive to recompute, and every time you have to do your policy gradient, you have to recompute it. Yeah.
Well, and we also need to use the Monte Carlo estimate.
Yeah. Yeah, exactly. So you have to compute grad log pi transpose with autodiff, and then you're going to take an expectation with Monte Carlo, and then you're going to invert it.
How do we know that this second order approximation has good enough?
We don't. Like with most things, I think you make an approximation and then you like choose a small enough step size that approximation is not so. Yeah. Like it's going to be really crazy if you're like if your KL divergence is like super, it's like super highly curved, right? But within a small enough epsilon, like it can look approximately whatever.
Is there a way to like parameterize your policy such that it's not highly?
It's hard with neural nets to do that, I think. At least I don't know of a way to do that. It's a good question. Cool. So this is a paper from like 2008 from Jan Peters, but they show that if you can use the natural policy gradient, you tend to get like significantly more efficient performance than vanilla policy gradient, things where not preconditioning by the Fisher information metric inverse. And you tend to be able to like run it on real robots to do things like ball and cup or play baseball and so on. Yeah. Natural policy gradient is this thing where you're multiplying by F inverse. Yeah. It's PSD, right?
But you can have zero action.
Yeah, you'd usually add like some regularization to make it invertible. Actually, shouldn't it always be invertible if you have grad log transpose? I guess you're taking the expectation, and so that's what make it not. That's what might make it non-invert. So in practice, you would add some regularization to it. But let me get back to you on that. I don't want to bullshit you on that. Remind me of your name.
Wait.
Wait. Okay. I'll send an EdStem post about that. Thanks. Okay. So just to recap, the second concept we went over is we started with the gradient descent, which is ascent of the linear approximation with the quadratic constraint, which is under the Euclidean norm. We said it's going to be better if we do it under a different norm, let's say a G norm. We didn't know what G was, so we said we're going to take a KL divergence between pi theta and pi theta I. We will approximate the KL divergence by second order approximation, right? And we said that that's going to give us the Fisher information matrix. And then we're going to multiply it by Fisher information inverse. That's going to rescale the parameters. Right? So you're not sensitive to parameterization. Okay. Any questions so far? Make sense? Cool. So that nobody uses national policy gradient today, right? So why not? Like, what makes it fun? So the first thing, which is maybe the most obvious thing, which Ray was also asking, is that, well, he was asking if it's BSD and invertible, or positive definite and invertible. But in general, it's like a huge matrix inversion, right? And so you have like, let's say you have a big neural net, your F matrix becomes D by D. And so it becomes pretty hard to invert explicitly. And so you want to kind of avoid matrix inversions like that. And the second is our original issue of like step size, like we were getting at, we still haven't dealt with our step size issue, right? And so the next algorithm we're going to talk about is called TRPO, or Trust Region Policy Optimization. And it's going to try and deal with these two issues. Okay. So the other issue, which is maybe a side note, is that you're still only taking one step every time you collect some data, right? And so you still like are not reusing any data. So you're not off policy at all. But we're going to primarily try to deal with these two issues. How do we avoid matrix inversion? And how do we deal with this like step size issue? Okay, so there's going to be three key ideas in PRPO. The first is that we're going to try avoiding this matrix inversion with this idea called conjugate gradient, right? The second is we're going to go from just doing on-policy updates to doing constructing a surrogate objective, which is like an importance sampling objective, which allows you to use old data. And the last thing is we're going to apply backtracking line search. Right? So we're going to apply something to choose the step size better. And so that's going to lead to results that look like this, which is one of the first things that shows that model-free RL can successfully learn to walk with characters and animation and so on. Cool. Okay, so let's kind of run through these. There's lots of different ways of looking at PRPO. The paper is kind of hard to read, in my opinion, but this is how I think about it. So the first thing we want to do is we want to like avoid having to compute F inverse, because all we really care about is F inverse G, right? So we don't actually care about F inverse, we only care about F inverse G. And so the first thing we want to do is instead of getting F inverse explicitly, which is matrix inversion in D by D, right? So we're going to try and convert this into a more tractable problem that avoids ever computing F inverse explicitly. Okay. Yeah. Sorry. Yeah. F inverse is going to be your expectation grad log transpose, and G is going to be expectation grad log times R. Yeah, good question. So you can kind of think of this as this is your gradient, and this is the thing that's rescaling the parameter terms so that they matter equally to the function. Right? Okay, so what we're going to first do is we're going to try and convert this problem where we're explicitly computing F inverse into some sort of an iterative minimization problem, right? So essentially what we want to solve is the solution to this problem Fx equal to G, right? Fx equal to G will give us F inverse, X will be F inverse G. And you can show it's the same as the minimum of this quadratic problem, right? You can just take the gradient of this, which is like Fx minus G equal to 0. Just take the gradient of the quadratic. Fx minus G equal to 0 means Fx equal to G, which means that X equal to F inverse G, right? And so if I want to find X equal to F inverse G, if I can just solve this minimization problem, then I will get X without having to compute F inverse, right? And so the trick in conjugate gradient is that you start by converting this problem where you have to invert F to just solving this minimization problem iteratively, and the optimum is F inverse G. And so like the first thing we do is there's no conjugate gradient. We're just saying we want to get F inverse G. So we're just going to solve this optimization problem. If we can solve it, then we will get F inverse G. And the second thing we're going to do is we're going to use this algorithm called conjugate gradient. It's a little bit painful to explain in class. So I would recommend going through this, this tutorial, but maybe I'll provide the intuition here, right? If you think about coordinate descent, right? Coordinate descent, you can think of it as you go in one direction, then you go in another direction, then you go in one direction, then you go in another direction. Whereas gradient descent is you're like taking the steepest descent. Coordinate descent is you're doing one direction at a time, right? So conjugate gradient is kind of like a version of coordinate descent, but you're doing it not in orthogonal directions, but in F orthogonal directions, right? So you're saying that like if you have a matrix F, so you're trying to, that is like the conditioning for your quadratic, right? When you're taking steps, you're choosing descent directions that are F orthogonal, which means that your descent direction, I think there's a typo. That should be J. But like, let's say your descent direction at one time step was dj, the next time step was di, right? You're gonna like choose a descent direction that is F orthogonal to the previous step, right? So you can kind of think of it as like, if F was identity, then conjugate gradient would correspond to coordinate descent, right? So you're saying I'm going to just take a step in one direction, then another direction, then another direction, then another direction, right? And what conjugate gradient does instead is it says we're going to like choose basically descent direction di and di plus 1 so that they're like F orthogonal, which means that they're orthogonal when projected on the geometry of F. So if you think of F as something that warps the geometry, right, to be a little curvy, you want them to be like F orthogonal, which means that the dot product on the F norm is 0. And so you can kind of think of it as like, you really don't want the step in one direction, in like one descent step to hurt the next descent step. And so the reason to do this is just because it's efficient. When your matrix F is sparse, you can show that this algorithm is pretty efficient. And you never ever need to compute F inverse, right? So you just get away with computing essentially an iterative solution that looks like coordinate descent, but you're avoiding computing F inverse. Yeah. Yeah, yeah. But it doesn't, it basically is not that fast if F is not sparse, or it only works on certain Fs, basically, or it only is efficient on certain Fs. Okay, so the first big idea in TRPO is just like avoid computing F inverse by converting it into a minimization problem. And for the minimization problem, do it efficiently using this conjugate gradient algorithm. You could do it with any other efficient iterative minimization problem, but you want to avoid F inverse computing it explicitly. Yeah. Cool. So the second idea is to say, choose the step size. Like we were talking about, we want to choose the step size so we don't make too big of a step, right? And so the problem with gradient descent is that if you choose the wrong step size, because you're doing a linear approximation, you may like step too far and you might have things that start decreasing, right? And so what we're going to, the basic idea of backtracking line search is you start with a large step size and then you keep backtracking. Your large step size may lead to a decrease in value. You keep backtracking until your step size is small enough that you lead to an increase in value, right? So you start with something big. You can kind of think of this as start with something big. You compute the descent direction or the ascent direction. You take a big step size, and then you like backtrack it down until it's an ascent, right? And so you can say that, the first step, I went too far, so it is like reduction. And then I'm going to like reduce, and so maybe it's an ascent, and I can reduce some more, and then it's an ascent, right? And so the idea of backtracking line search is start with a large step size and then reduce it with some multiplier less than alpha until it's an ascent. Yeah.
You just reduce and multiplier, or you do like binary search where you have like middle.
You often just choose a multiplier which is between 0.5 and 1. Does it make sense to do it sequentially instead of that? I guess you could also batch it, but like how would you, like you're just saying do random search on steps?
So let's say so you have let's say alpha is your biggest one, let's say 0.5, 0.25, 8, 16.
You could do that.
Then is this one.
You could do also, yeah. So you don't have to be each. Yeah. But
So are we still ping-ponging around?
so this is within a single step, right? So it's like this is not between steps. It's saying like I've chosen a descent direction, and within that descent direction, I'm just seeing how much of a step it is. Right. So if I like go back to my ascent, right? So it is just like letting me choose that alpha basically.
Does it matter as long as the next, as long as we get into the ascent one previous step? So even on like the other slide, even like that first image, we're still getting like.
Yeah, the first image I've got to change, but like this number should be like down here.
Okay.
Right. If it's like a not an ascent, like then you backtrack. Yeah. So usually what you'll do is you like backtrack until you have like ascent more than threshold. So you want to say that it's like your evaluation of your function at whatever theta I plus step size times your gradient direction is at least alpha better than your current evaluation.
This seems hard because like you have to evaluate the policy and it's in a like high variance concept.
Right. We'll do that in the third piece. Is going to help us deal with that. That's a great question. Okay. Any other questions, thoughts? Okay, let me at least first go through it and then we can talk through the rest of the questions. Okay, so you're going to choose some multiplier between this should be 0.5 and 1. And you're going to compute the search direction, which is going to be F inverse G, right? We compute it from conjugate gradient. We're going to have search direction. Now you just want to see how far you want to go in that search direction. You're then going to start by finding the step size that maxes out my quadratic constraint, right? So my quadratic constraint, if you remember, was half theta minus theta I transpose F theta minus theta I less than or equal to epsilon, right? If you remember natural policy gradient, we had this quadratic constraint, which is the second order approximation to the Taylor to the KL divergence, right? And so if I set theta to theta I plus Ts, right? I plug it into here. I'm going to get Ts half Ts transpose F Ts is less than or equal to epsilon. So to find the maximum step size, we're just going to set this to an equality. And we're going to solve for t, right? So you can show that this is half t squared S transpose Fs is equal to epsilon. And so move things to the other side, you see t is equal to square root 2 epsilon by S transpose Fs. Right? That's the maximum step size you're going to start with. And then you are going to say that while while your evaluation, which we'll talk about in a second, of theta I plus ds is less than j theta I plus, like, let's say some alpha, right? Some threshold you want to improve by. You're going to keep reducing your step size by some multiplier beta, right? So you're going to keep reducing it. You're going to reduce it, evaluate it, reduce it, evaluate it, reduce it, evaluate it till you find an ascent. Right? And so all that backtracking line search does is helps you choose something so that you're not stepping too far. Okay. Good. Okay, so the second step is this element of t equal to beta t is your backtracking. So the second idea in ERPO is first we did conjugate gradient, so we avoided computing F inverse, and we used a coordinate descent like algorithm to find F inverse G. The second thing we did is we said we're going to do backtracking line search, right? And so with backtracking line search is going to help us not take too big of a step size. The problem with taking too big of a step size in reinforcement learning is that if you like step too far, your data becomes shit. If your data is shit, you like never recover. It's like it's like how do you say, vicious cycle, right? It's a vicious cycle if you step too far. And so you really don't want to take too big of a step size. You typically want to have smaller step sizes. It'll get you there eventually, whereas if you take a bigger step size, you just don't converge. Okay. And then, yeah.
Before you go on.
Yeah.
It seems like if we constrain the steps to only be increasing, we don't get the advantage of like stochastic gradient descent where you're able to escape like tiny local optimums.
But your gradient is still, as in you're still computing this with with batches, right? You're not doing like full batch. You're still computing like your gradient with a mini batch.
That's right.
And so there's stochasticity in that anyways. Okay, so the last point is the one that Alexander just brought up, is like if you have to do backtracking line search, that means you have to keep evaluating J at theta I plus ds, where T is different, right, in different points. But I only took samples once. So am I going to just keep taking more samples every time I want to do backtracking line search? And so the issue here is that every time I want to evaluate J of theta I plus ds, I have to like recompute it by taking samples in the world, right? Because if you remember J is the expected sum of rewards under your policy, right? And you have to run your policy to get the expected sum of rewards. And that's kind of a pain. So the question we're going to ask is, how do I do backtracking line search without having to recompute my policy all the time? Or resample from my policy. So I'm going to recompute my policy. I just don't want to have to resample. And I just want to have to take a set of samples and then be able to do backtracking line search without recomputing or without resampling every time. Cool. All right. So the question we're going to ask is, how do we evaluate J theta or J theta I plus ds, right, at different values without having to resample in the environment? All right. Ideas. How do we do that? Remember, J theta is expectation of states coming from d pi theta of s, actions coming from pi theta a given s, like sum of rewards. Yeah. So I want to like compute this for new thetas, but I don't want to have to resample from the thetas. How do I do that? Jesus Christ. Tell us what important sampling is, Harin. That's right. So the idea of important sampling, which I foolishly gave away as a solution, is to say that if I have expectation under some p theta, I want to be able to compute this expectation if I didn't have access to samples from p theta, right? Let's say I had access to samples from some q theta, right? How do I compute the expectation under p theta if I only had samples from q theta? Okay. Are folks already familiar with important sampling? Ish? Huh? Did I talk about it last lecture? When was I talking about off policy gradient last lecture, or when did I bring it up? Okay, I'll say it again. But the idea behind importance sampling is to say that if I have an expectation of r tau under p theta tau, right, I can always write it. I can multiply and divide by q tau, right? And I can write as an expectation under q tau of r tau weighted by p theta tau over q tau. Right? And so the way it's going to fit into our picture here is that I'm not going to have samples from every theta that I'm going to evaluate, right? So let's say my theta I was my previous iterate. So I have samples from theta I, but now I made an update to theta I, right? Now I don't have samples from theta I plus ts. I only have samples from theta I, right? So if I can compute p theta I plus ts of trajectory divided by p theta I of trajectory, then I have the importance sampling ratio needed to evaluate my policy, right? And so I can do backtracking line search because I know that I can like get, if I can get this ratio, then I can just reweight the expectation to get my J, right? So the question is, how do we compute p theta over q for our particular choice of p theta and q, right? And so, okay, how do we compute? We're going to choose a particular type of q. We're going to choose a particular type of p theta, and we're going to show that you can use importance sampling to do this. All right, so given importance sampling, specifically what we're going to try and do is we're going to set p theta to p theta I plus ts, and we're going to set q theta to p theta I, right? So it's going to say that I've taken samples under theta I. I want to evaluate theta I plus ts, but I don't want to have to retake samples from theta I plus ts. So if we're going to plug this in, right, the first thing we're going to do is we're going to write p theta tau. So in our case, we're going to say p theta tau is the initial state likelihood multiplied by the dynamics multiplied by the policy by theta. And let's say you had some q tau, which is going to be initial state likelihood multiplied by the dynamics multiplied by q. Right? The world is the same, right? You're in the same world, you're in the same initial state distribution. The only thing that changes is the policy, right? If I have two policies that are running, let's call it p I theta to at given st and q of at given st. To get the ratio between their trajectory distributions, I just need to divide these two, right? And if I divide these two, then I can cancel the initial state distributions. I can cancel the dynamics, right? They're the same. And so you can write the importance sampled objective for some p theta tau under q tau as a product of pi theta over q at every single time step. Right? So you can say that like if my trajectory is t time steps, I compute pi theta over q at every single time step and multiply them to get my importance weights, and I can compute the expectation under p theta tau just from trajectories from q tau. Okay. Everyone with me so far? Okay, so what makes this tough? Like, why shouldn't I do this all the time? Yeah. Does Q have support everywhere? It may not, right? Are there other reasons we should do this all the time? Sometimes when you have support issues, you can flip things, right? So you don't able to see. Are there other reasons this is a bad idea?
The more the take of policy, the more different the distribution.
Right.
So yeah.
Your approximation becomes worse, but also numerically, you're multiplying a bunch of ratios of probabilities. And so importance weights are super high variance. And so you're multiplying these like numbers that are like less than one altogether, right? And so any small errors will become like big issue. And so in general, like an importance ratio over a whole trajectory becomes quite unstable and high variance, right? Because you're multiplying a bunch of tiny probabilities. And so we're going to try and come up with a different objective that is a little less unstable. And so the idea behind TR0 is to say that we're going to do importance sampling, right? So we're still going to say we want to compute this kind of expectation under p theta tau, but we're going to do it without having this like product over the whole trajectory. We're going to try and do an importance ratio, which is not a product over the whole trajectory. Yeah. Okay, so we're going to try and rewrite this in a slightly different form. So if you remember the stationary distribution, right? So you can say that like the return is saying state sampled from p theta s, an action sample from pi theta a given s of q, right? Q is your expected, is your sum of returns in the future. And if you do this, important sampling would say, let's say you were trying to evaluate some j theta where you only had samples from p theta I. Right? So you didn't have samples from p theta, you only had samples from p theta I, right? You can write the importance sampling ratio as p theta s times pi theta of a given s divided by p theta I of s times pi theta I of a given s, right? So this is the state distribution. This is the action distribution, right? And so if I wanted to, the expectation I want to compute is under p theta or p theta pi theta, and I only have samples from p theta I, pi theta I, right? So you do the same importance ratio trick, but you're going to have like one ratio, which is the state distributions, and one ratio, which is the action distributions, right? Okay, so the trick in TRPO is to say, pretend that p theta and p theta I are not that different and cancel them out. And so what they're going to say is that basically ignore the ratio between p theta and p theta I, make it 1, right? And so you're going to optimize this thing called the surrogate objective, which is essentially going to ignore the difference in state distributions between p theta and p theta I. Yep. And so the objective you're going to optimize is you're going to sample states from p theta I. You're going to sample actions from pi theta I. You're going to weight it by pi theta over pi theta I, but you're not going to weight it by like, this term is the one that has all the numerical instability because it's over multiple steps. And so you're going to say that this term is basically 1, right? And so essentially what you're doing something slightly wrong, right? You're saying that like, I'm going to like essentially say that the distribution of states under theta and theta I are approximately the same. But the argument in TRPO is that if your states are not, if your policies are not changing that much, that is not that horrible of an approximation to make. Right? And so what they show is that you can construct this surrogate objective, and this approximation holds with like a small bound as long as pi theta and pi theta I are not that different. So they're like bounded. Right? And so the gap between this approximation and the true objective depends on the divergence between pi theta and pi theta I, right? And so the one way to think about it is pi theta and pi theta I were the same. These two distributions would be the same, right? But if they're different, this distribution goes with like something that goes like the squared of the total variation divergence or the KL divergence between pi theta and pi theta I. Yep.
This is going to put it in the national policy.
Can you repeat that?
They don't know how it's going to put it in
Yeah,
national
exactly.
policy.
That's why it makes sense.
Okay.
That's why it makes sense. So you're already doing the national policy again, which is constraining the KL between the policies. And so that approximation is not that egregious. Okay. And sometimes in TRPO, you'll replace Q by Q minus V. So V is again your baseline, right? Your credit. And so Q minus V is often called the advantage. Like saying how much better is a particular state action pair than the average state action, average action at that state. Right? Okay, so this is often called your surrogate objective. You can think of it as you're sampling, for given your current policy, you're sampling states, you're sampling actions, which means you're just running trajectories, right? For every state and action that you sample, you compute pi theta over pi theta I. You multiply it by your Q function or your advantage, which is a sum of returns from there till the end, right? And then you can take the gradient of this thing with respect to theta, and that is your gradient. Yeah. So everything that we were doing with J theta earlier, we're just going to replace with the surrogate objective. And what that's going to allow us to do is it's going to allow us to evaluate the backtracking line search at every single step without having to resample. But you can't like take huge steps. You have to take bounded steps. Okay. So that's the basic idea of TRPO. There's 3 key ideas. The first is you're going to avoid matrix inversion with the conjugate gradient and making it iterative minimization. Second is you're going to do backtracking line search. And the third is you're going to have an important sampled objective, which allows you to evaluate it without having to continuously redraw samples. And here's a video from the original TRPO paper, but they show that it can be pretty effective back in 2015, before we actually knew how to do any RL, on like a bunch of fun simulated characters on Atari games, on lots of domains, even with the somewhat egregious approximations. Fun anecdote is actually, I think a lot of these Mujoko creatures came out of UW. They came out of Emo Todorov's group here at UW, but they were developing a bunch of these motion animation methods here. Cool. Alrighty. Let's pause here for a few minutes and we will start in like 3 minutes.
Big question. I feel like so it's something that the state probabilities are the same. Suppose there's some state that gives you like a tournament reward, and your new policy slightly increases the probability of making it to that state.
You're ignoring that dependence.
You're ignoring.
Yeah.
So it wouldn't be able to update it towards.
Yep. Right. You're accounting for at every state you're ignoring how like theta affects reaching high reward states, but you're accounting for things in the future from there. And so you're ignoring like that small term. So that's why it's like if you're doing it completely properly, right? You would have both terms, p theta and p theta I. So you're not like completely ignoring the effect because you would cancel both terms, but you're ignoring some of the effect.
And that effect is high policy, like I guess
That's
long horizon.
long horizon, yeah, that becomes high. Yeah. And that's why you often will like so there's like tricks in PPO and TRPO where you like restart at intermediate states and that shortens the horizon. And so those kinds of things help. And then the other thing is you have to keep the policies pretty close to each other. Otherwise, this approximation is egregiously bad.
Okay.
Yeah.
Okay. This is one of the leading
So not anymore, but TRPO goes into PPO, which is the leading end. Okay. Let's keep going. So TRPO seems reasonable, but nobody uses TRPO in practice, right? So what gives? The first thing is we've kind of ignored how we've computed these advantages, right? We've said that we're gonna compute them with like Monte Carlo samples or Monte Carlo samples minus some values, right? And so we're gonna say that advantage estimation might be too high variance. And the second is that your optimization here, like the second order thing, even if you do conjugate gradient, it's like a little too much, right? So the idea behind the next class of algorithms is to like take this second order method, things that have to like do or pseudo second order method, things that have to do or Fisher information matrix inverse, and like try to avoid that, but kind of get the same effect. And so the first thing we're going to do is we're going to try and have a different advantage estimator, which is called GAEs, or generalized advantage estimation. And the idea behind GAEs is saying that if I want to compute advantage, right? So advantage is the difference between the sum of rewards in the future and the average, right? Average returns for actions at that state. So the typical advantage estimator looks something like this. It says that it's reward plus gamma reward at the next step plus gamma square reward at the next step until gamma to the n minus 1 reward at Rn minus the average reward at the first stage. Right? So this is kind of like your sum of rewards in the future for a particular action, right? For a particular trajectory. And then this thing is kind of like what's the average? And you're looking at the difference between a particular, the average. Okay. But what GAE notes is that this might be particularly high variance because you're taking still a single sample estimate, right? You're still saying that this is the sum of rewards along a particular trajectory. Right? So you're still taking a single sample estimate with high variance. And what they do instead is they say that this is one of a broader class of advantage estimators, which go like this, right? So you could say A sub n of S1A1 is basically R1 plus gamma R2 plus gamma R3 till gamma to the n minus 1 Rn but no terminal value, right? So it's kind of like you're saying, if it's an n-step reward, you're just summing up the rewards and then subtracting the value from subtracting the value of the first state, right? So you're saying, I'm going to sum up these rewards along the whole trajectory, and I'm going to subtract the average reward. That's an, right? A sub n. A sub n minus 1 is saying that let's sum up the rewards till the n minus 1th point, and then let's add the value at the last step. A sub n minus 2 is going to be, let's sum up the values till the n minus 2th step, and then let's add the value for the last two steps, right? And so what it's saying is that let's use a function approximator to replace part of the trajectory. Right? And taken to its logical extreme, A sub 1 is you're going to like take the first reward, right, in a trajectory. You're going to take the first reward, and then you're going to substitute everything else in the future with the value function, right? So the value is going to tell you how well you're going to do from that state onwards. And so you could say A sub 1 is R1 plus gamma VS2 minus VS1, right? So you're going to say first reward, this is S1, this is S2. So you're going to say R1 plus gamma VS2 minus VS1, right? And so you can say, you can think of it as like you're replacing variable amount of the trajectory with the value function, right? And so on one extreme, you have none of the trajectory replaced with the value function. So here you have none replaced with the value function. Here you have essentially all replaced with the value function, right? And so you kind of have a family of estimators, and they have different characteristics, right? And so what you'll have is that the n-step advantage is unbiased, right? So you have like low bias, but you have high variance, right? And the reason you don't have bias is because you're not adding, and we worked out why subtracting a baseline is unbiased, right? And so this is just like the completely unbiased estimator. Now I've like added this value function. This value function can be wrong, right? And so this estimator is biased. And so you can kind of think of this as, but this is low variance because you're using function approximation for V. You're not just saying it's a single sample estimate. And so the lowest estimator here, the A1, is the lowest variance, but it's the highest bias. And the one on top is the lowest bias, but it's the highest variance, right? And so the idea behind GAEs is to say you're going to take a bunch of these estimators, and then you're going to combine them as a geometric sum, right? So you're going to say that like, rather than having, like, so far we've kind of been considering this extreme, right? We've been saying like, we're only going to consider A sub n of theta. And so instead what they do is you're going to say, I'm going to consider geometric sum with some parameter lambda, right? And lambda is telling me I'm going to compute each of these estimators, and then I'm going to take a geometric sum according to lambda, right? And so lambda equal to 0 means that I'm going to be at the one-step estimator. Lambda equal to 1 means that I'm going to be at the n-step estimator, right? And anything in between is like interpolating between them. And so the idea behind GAEs is that it gives you a good way to trade off bias and variance. And by setting lambda with some intermediate value, you get a better bias variance trade-off than any of the extremes. And so it's a similar idea to things like eligibility traits. You all have seen this before. But what they show in their work is that if you look at, this is the the cost, so you want it lower to be better. Like you see that like the best lambda is not 0. Is not 1, like this orange line is 1, but rather it's like 0.9, 0.92 or something here, right? So you can see the like the best cost reduction is like when you set lambda equal to something close to 1, but not quite at 1. Right? And so the idea here is basically you're just using function approximation to reduce some of your variance. And you're saying rather than having the whole trajectory be summed up, you replace some portion of your trajectory with function approximation values. Right? Yeah.
So to be clear, the R's, are they taken from like Monte Carlo?
The R's are taken from Monte Carlo, and then you like tack on the V at the end of them. So it's like you take take K steps of R, and then you tack on the V for the rest. Yeah, it's very similar, but it's not off policy, it's still on policy. So the idea of temporal difference learning, which we'll cover next, is that like you can compute this from not the latest batch of samples. But so far, we're going to compute all of this from the latest batches. Okay, so this idea, sorry,
Yeah, so for the bias variance trade-off.
Yeah.
In the advantage cross estimation, do you explain again why like different, like.
Different estimators have different bias?
Have different, variance.
Yeah,
The-
so
That value function also fine.
so one way of thinking about why a value function reduces variance is like imagine that you had many trajectories, okay? And so you had like one trajectory that goes like this, maybe another trajectory that goes like this, and another trajectory that goes like this, and another trajectory that goes like, right? So if I was only considering value along my single trajectory, I like cannot use this or this or this, right? I just use my own trajectory. Whereas if I had a value function, I'm using function approximation, right? So I'm saying that I'm going to like compute the value on at this state from this trajectory, this trajectory, this trajectory, and this trajectory, right? And so you're like sharing information across the trajectories. That's why you reduce variance. That's you're like borrowing information from other trajectories because of function approximation.
Is lambda generally less?
Lambda is generally less. What would you do with it?
I mean, like you're weighting the earlier ones heavier with lambda less than 1. Why, like, why would you not want to weight the low variance ones more?
Oh, because they're biased.
Okay, so you're just more afraid of bias than you are
Yeah.
of variance.
Yeah, exactly. Especially at the early parts of training, like you're quite biased. As you go further along training, you're less biased. And so then you might, in practice, you don't shift it a lot, but you could. Yeah, I don't actually know what happens. It's a good question. Okay, so that's TRPO. Just to recap, we had 3 ideas. Conjugate gradient, backtracking line search, and a surrogate objective. And then we talked about this idea called GAE, which just takes different these are called bootstrapped estimators because you're like taking k steps and then bootstrapping the rest with the value function, right? And so you have different levels of bootstrapping that you like take a geometric average of, right? And so that is GAE. How are we doing that? We have done all that. Okay, cool. All right, so that brings us to the algorithms that we use today, which is proximal policy optimization of PPO, right? And so the idea behind PPO is we really want to avoid that like that H inverse G term, right? Even with conjugate gradient, but you still want to like the general vibes of PRPO is that keep the policy close, and then take a step. Right. So, can you explain why oh, because like you're estimating with finite samples. So if I had like infinite samples, then I would get something like that. Like basically, if I have infinite samples, then the value function converges to the true sum of returns. But if I don't have infinite samples, then it's going to be something. And so like even if I take more samples, if I have like a wrong value function, it doesn't give me the right number. So expectation. But in expectation is percent. In expectation is the value function. Yeah, but then you have an expectation inside an expectation. Like it's like you're computing R plus an expectation, and like that that thing itself is wrong. Let's chat about that. Okay, so the idea behind PPO is that instead of like doing a trust region, which is what led us to this like F inverse G update, right? We're going to just directly control how much the policy changes. And so we're going to say TRPO on natural policy, we can do this like KL constraint. The KL constraint gives us this like second order approximation. The second order approximation gives us this TRPO and PG update, right? It gives us F inverse G term. And we're going to go from there to a much simpler objective, which is PPO. And so we're going to replace this kind of constraint optimization with just a clip. And you never do any second order optimization. You just have first order approximation with the clipping, right? And so both of them, in terms of vibes, are restricting how much the policy moves, right? So you're taking this ratio between pi theta and pi theta I, and you're clipping it. So you're saying that like my pi theta can't change more than some value, right? And it's not exactly the same as scale, But in both cases, you're restricting how much the policy moves. Yeah. Yeah, exactly. So you're taking the ratio between pi theta and pi theta I, and you're saying you're clipping it between 1 minus epsilon and 1 plus epsilon. And so the main idea of PPO is to say that you want to restrict the policy rather than having this like expensive second order thing. Why don't you just do something simpler, which is clipping pi theta over pi theta I? If you can clip pi theta over pi theta I, if pi theta moves more than 1 plus epsilon away from pi theta I, the gradients go to 0 because you get clipped, right? And so you don't move. And so the idea behind PPO is very simple. It's just constructing a very similar objective. If you remember our surrogate objective, it is basically expectation under pi theta I of pi theta over pi theta I times the advantage, right? But we were doing this under the constraint that pi theta and pi theta I are less than epsilon, right? We're saying we want to KL constrain things. And rather than doing KL constraint, you just modify this objective to this clipped objective, right? So we'll unpack why there's like a minimum in a second, but like just look at the second term. It is saying like you take the ratio, let's call this thing R, ratio between pi theta and pi theta I. You don't want it to change too high, you don't want it to change too low. So you clip it both sides by 1 minus epsilon, 1 plus epsilon, and then multiply by the advantage. Right? So if pi theta changes more than this epsilon, then you don't have any more gradients. So you don't let it change more than that. Okay. So the nice thing about it is that you are taking, because you have a surrogate objective, you can do multiple steps. So typically in PPO, you'll take like mini batch steps. You don't do a huge gradient update with a huge batch. You'll have many mini batch gradient steps. You don't have any second order optimization. There's no conjugate gradient. There's no nothing. Just add them. Right? Use your standard optimizers. It's like super simple, super stable. It is important to choose the right epsilon. Right? Like a lot of times you choose epsilon as 0.2, but you can kind of constrain how much the updates will be. So the key benefit of it is that it's super duper simple. Okay, so this objective looks, if it is just clipping, right? Like it's a little bit confusing to have this like minimum here, right? And so the idea behind the minimum is that you want to have you want to be like pessimistic about large improvements, but you don't want to like ignore things that are harmful. Right? So let's consider two cases. And so let's say the advantage was positive. Eric, do you have a question?
Yeah, is there a mathematical motivation behind like 1 minus epsilon and 1 plus epsilon specifically versus something more explicit like epsilon and 1 over epsilon, or it's just like a convenience?
As far as I know, it's a convenience, but yeah, I don't think there's anything that profound. Okay, so let's consider two cases. The first case where the advantage is positive, right? So let's say your advantage is positive, which means your action is good, right? Action is better than the average, so you want to increase its likelihood, right? And so if your ratio goes greater than 1 plus epsilon, you're saying like, okay, like you want to increase it, but you don't want to increase it more than 1 plus epsilon, right? You're saying, I don't want to increase it too much. I don't want to be over optimistic. But what this objective would do is if your ratio is less than 1 minus epsilon for positive advantage, you're going to like, which means that you're assigning too low of a likelihood to good actions, right? You're going to keep penalizing the fact that you're assigning too low of a likelihood to good actions. So it's kind of asymmetric in the sense you want to like cap increase on the good side. You don't want to be over optimistic. But if you're like falsely assigning low likelihood to good actions, you want to like penalize that behavior. And on the other side, if your advantage is negative, which means that you have, if you have bad actions, right? What you want to say is, if your R is less than 1 minus epsilon, which means that you're like reducing its likelihood, right? You want to say that you don't want to reduce it way too much. You want to clip how much it moves. But if you're like falsely giving it really high likelihood for something that is bad, like keep penalizing giving too high of likelihood to something that is bad. Right. And so that's kind of the logic behind this, like slightly more convoluted objective. Okay, so before we end, here's some examples of PPO on robotics problems. So you find that it works super well in these physics simulators like iSig and iSig because you can parallelize batches a lot, right? So you can say, construct a huge batch size, I can sample a lot, and that gives you like nice dexterous behavior. But you can also get it to work for like high-dimensional video games like Dota and StarCraft and so on. And so the nice thing is the same algorithm tends to work across a broad variety of domains. Okay, I think let's stop here and we'll cover the rest on Wednesday. Thank you.
So with the
Cool. Here's some really interesting ideas.
Nice.
I'm actually about to go again.
Great.
But are, yeah, that's an all extension of the project.
Yeah, I think it's fine.